When site reliability engineering teams attempt to rein in the spiraling costs of log management, the first instinct is often to squeeze the data. The assumption is that pushing telemetry through a generic compression algorithm, condensing massive data streams into a single, dense cube, defends against ballooning storage bills. It is an understandable reflex. Standard utilities like gzip are ubiquitous across the industry. They cost nothing to implement and genuinely shrink the footprint of cold storage archives. However, treating compression purely as a storage solution creates a massive hidden compute penalty when you actually need to use the data. Because generic compression renders data completely unreadable, you cannot query it directly. Executing a search against an archive triggers a massive volume spike, forcing your system to reinflate gigabytes through an expensive compute node, and it rarely stops there. To make that data searchable, systems require it to be re-ingested into a separate search index, incurring a second, heavy compute penalty. Resolving this bottleneck requires a modern, structural approach, one that reduces data volume by an order of magnitude without breaking native queryability. Relying on tools like gzip for observability data merely shifts your bill from a predictable storage cost to a highly unpredictable, punishing compute cost. To understand exactly why this bottleneck exists, we have to look at the algorithmic mechanics of how a general-purpose compressor processes a data stream. Algorithms like deflate operate on a sliding window principle. They are designed to scan arbitrary text files in a single pass as the data flows through. The algorithm has a narrow job. It looks at a sequence of bytes and scans backward through its memory window, identifying repeated, arbitrary sequences. When the algorithm successfully matches a sequence, it replaces the repeated text with a much shorter symbolic reference, immediately saving space. Applied to text-heavy application logs, this generic method performs adequately, typically shrinking the file size to roughly a third or a fifth of its original volume. This method fails to exploit efficiency because the compressor treats the incoming data as anonymous bytes, operating with zero awareness of the structural context of the information. By destroying that original context, the algorithm transforms the compressed file into a single opaque blob. Directly querying this solid block for a specific latency metric or a specific error code is mathematically impossible. The structural boundaries of the data no longer exist. To find a single failing request line, the system has no choice but to decompress the entire blob back into raw plain text. General-purpose algorithms optimize for random text. In doing so, they destroy the structural accessibility required for rapid search. Moving beyond these limits requires looking past the algorithm itself and examining the physical reality of telemetry. Logs, metrics, and traces are not novels or random human-written sentences. They are highly rigid, highly structured outputs generated by machines. This visualization shows standard machine-generated JSON application logs. Looking closely at the output, the inherent entropy of the data becomes obvious. The first major mathematical pattern is repetition. Identical static message templates repeat millions of times within a single hour. Within those millions of repeated templates, only a tiny fraction of the actual fields, perhaps a single IP address or an active user ID, change from line to line. The second pattern is predictability. Time-based data always marches forward in a highly regular sequence. The third pattern is clustering. Specific numeric fields, like server response latencies, consistently cluster and trend together within narrow statistical ranges. When you extract fields of the exact same data type, they share deep mathematical properties. A generic text scanner, looking only for exact byte matches in a sliding window, is completely blind to these relationships. By failing to recognize the rigid rules governing machine-generated data, standard compression algorithms leave the vast majority of potential storage efficiency untouched. Exploiting these patterns requires an architecture designed for the data's properties, such as the patent-pending system developed by Sasquatch Labs. Rather than running a single generic pass over the data, this system applies multiple distinct processing layers, each one tuned specifically to the inherent structure of the information. The first phase physically separates stable, repetitive templates from highly dynamic variables. Static templates are stored exactly once in a standalone dictionary. Even if a log shape appears 10 million times, its static text is replaced by a microscopic reference point. In the second phase, the system takes the separated columns of variable data and begins encoding like-typed values together. By isolating sequential time-based data into its own column, the algorithm can apply highly aggressive predictive encoding that expects the numbers to ascend. By grouping strictly typed numeric metrics together, the system can apply statistical compression models tailored specifically for calculating the delta between tightly clustered numbers. Instead of treating the log file as a flat sheet of text, the algorithm models the distinct mathematical behaviors occurring within every individual column. By exploiting these physical properties, the storage footprint shrinks by an order of magnitude or more. When you apply standard algorithms to 100 gigabytes of raw logs, you might reduce it to a 25 gigabyte block. Applying property-aware compression to the exact same dataset can push that footprint down to 5 gigabytes. On highly structured streams, such as security intelligence data, the reduction ratio climbs even higher. To be clear, achieving these numbers does not involve dropping data, sampling the stream, or discarding outliers. The architectural process is entirely mathematically lossless. Every byte of original telemetry can be reconstructed with perfect fidelity. Property-aware algorithms simply exploit the physical reality of telemetry, shrinking storage footprints well past the theoretical limits of a generic text scanner. But high ratios only solve half the equation. We have to return to the economic problem of the query phase. If your data is heavily compressed, but you still have to inflate it to read it, you have just traded a storage bill for a massive compute bill. This is where property-aware compression executes its most crucial function. Because the data has been deliberately organized into distinct columns and dictionaries, the structural boundaries of the information remain intact. To leverage this, Sasquatch Labs developed the Snowman query engine. The engine is designed to read these highly structured chunks exactly as they are. Instead of inflating massive text blocks, queries thread directly into the separated, compressed columns to extract precise results in place. The engine natively speaks industry-standard languages. Engineering teams can search using LogQL, SPL, TraceQL, or PromQL, extracting exact data points without translating existing syntax. This architecture completely eliminates the requirement to decompress the archive and re-ingest the data into a secondary index just to execute a search. By aligning the compression architecture with the structure of the data, teams can finally retain massive telemetry volumes for search without the hidden penalty of a second compute bill.